Okay, so the first problem we have to find all the solutions for each.
Okay.
So the first one is 2 cosine 2x minus 1 equals 0.
And all the solutions, not just the solutions in the unit circle?
No, then a couple later problems are that.
Okay. All right. Um, so, actually, it's a better problem if it is in the unit circle. When you're
Okay, well,
when you're
what we usually
taking
do in class. Oh, sorry.
when you're taking cosines of multiple angles like 2x, it turns out that there's something very special you have to do when they limit you to 0 to 2 pi. You have to actually double that and come up with all the solutions in 0 to 4 pi. And that multiple is whatever this coefficient is. But anyway, let's do this one. So what do we end up with? We end up with the cosine of 2x equals 1/2.
Mm-hmm.
Which means 2x equals inverse cosine of 1/2. Now what?
I don't know.
Well, what's the inverse cosine of 1/2?
The inverse cosine of 1/2 is pi over 6.
Yeah.
And,
Now hold it, it's pi over 3.
oh, pi over 3, sorry.
Yeah, cosine of 60 degrees is 1/2.
Yeah.
And let's figure them all. So let's list a few, and then maybe we'll pick up on a sequence.
Okay, another one is 5 pi over 3.
Yes. Fourth quadrant.
Another one.
Yeah, in other words, now to get the rest of them, add 2 pi to your first one. In other words, those are the two answers in the unit circle.
Mm-hmm.
So to get the next, it's got to be 7 pi over 3.
Yeah.
And 11 pi over 3. And we do indeed see a sequence. Now, that's 2x. So x must be pi over 6, 5 pi over 6, 7 pi over 6. So now define it
Oh, okay, I see.
as a k-series or n-series, whatever you use.
Um, 5 pi over 6, 7 pi over 6. So it'd be pi plus.
Oh, hold it. We can't do it, can we? In other words, we're going to have to do it as two different series.
Yeah. Wouldn't you have to do like a pi over 6 series and a 5 pi over 6 series?
I think we can connect those two, and then another one. Well, now hold on a second. No, what I'm really doing is connecting those two and
Yeah.
two. And that's the way I kind of like to look at it. And that's why I always do two unit circles to try to define these infinite series.
Mm-hmm.
So let's see, what would it be? So I'm connecting those two to start with. So what is
So that would be pi over 6 plus pi n.
Yeah, and in fact, it would be actually useful to have another one here. In other words, to add 2 pi to this, you get 13 pi over 6. And now you're connecting that, and now you can see how that series fits together.
Yeah.
N pi.
N pi.
And the other part of it, I don't know how they do this. I always write one below the other.
Yeah, they either way is fine.
So the other one is 5 pi over 6 plus
N pi.
pi also. Yeah. And am I right? I don't know. We discussed it last time that you have to use two different equations to define this series.
Yeah, that is correct. We've been going over that in class.
Now, some of them you get an answer that there is a single way, but not this. All right.
I just always have trouble with like finding the sequence or the pattern, kind of.
Well, the best way is to, like I said, write out, in this case, since I'm connecting this to this, that's only one. That doesn't really tell me the sequence is going to work. So I'm going to go there to there also, and once I get those first three terms, now I can come up with that.
Yeah.
And the same with the other one. All right, what else?
Okay, the next one is cotangent squared of theta minus 1 equals 0.
So we have cotangent squared of theta equals 1. What's the next step?
The next step would be to find the, or would you have to find the inverse cotangent?
No, not yet. We can't do that until we get cotangent theta isolated. Got to take the square root of both sides.
Okay, take the square root of both sides.
Which gives you what?
Just cotangent theta equals plus or minus 1.
Good. I say that because only about 5% of my students do the plus or minus. Notice that, just to back up here a second, I didn't actually have to do that first step. It's just easier to do. That's the difference of perfect squares, is it not?
Yeah.
Which factors into cotangent theta minus 1 times cotangent theta plus 1. And that's actually a quicker way to get to the solution, and you don't accidentally make the mistake of leaving off, although I guess we had the answer, didn't we? We had cotangent theta equal plus or minus 1, which would be your next step here also. So now what is theta?
Theta is all of the pi's over 4s? Okay. So that'd be pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4?
Question is that enough to assure the sequence? I think we need probably one more. 9 pi over 4.
Yeah.
Now that is enough. What is it?
Pi over 4 plus pi n pi over 2?
Or, yeah. And this one we can do with just one.
Okay. We
don't need two lines. I think that has to do with cotangents, if I'm not mistaken. Cosines you're always going to have to do in two different equations. I'm betting sines, no, sines you might be able to do. No, I think tangent and cotangents are the only ones where you can do with a single equation, a single infinite series.
Okay. Okay.
I don't know. You always find out. It's not like you need to know
Yeah.
that information. I was just recalling some of the ones we've done, and the fact that the period of the tangent and cotangent is pi is why I think that. Because it's pi, it chops up into a series that can be defined in one equation.
Yeah, yeah. Okay.
All right. What else?
The next one is 4 sine squared 3 theta equals 3.
Okay, work me through this. Still unrestricted domain?
Sorry?
Still
Oh yeah, still unrestricted domain, yes.
Okay. I'm gonna give you one next that restricts it just to show you.
My next one does restrict the domain.
And is it a multiple theta?
Yes.
Okay, good. We'll do this one and then we'll do yours.
Okay. First divide by 4 on each side.
Okay.
So that gives you sine squared 3a equals 3 over 4. Then take the square root of both sides.
Mm-hmm. Which gives you...
And that gives you sine 3a equals plus or minus root 3 over 1.
Over 2.
Oh, 2, sorry.
See why?
Yeah, because 4 squared
Square root
is
of
2.
3/4. Square root of 3 over 2. Also, that's one of your magic numbers, so you know what I mean? In other words, that's one of your answers for your unit circle all the way around. 1/2, square root of 3 over 2, square root of 2 over 2, those kind of things.
Yeah.
So, where is 3 theta equal to that?
3 theta is equal to sine, it would be pi over 3. All the pi's over 3?
Yeah, I'm just going to disprove what I thought before, aren't I?
Yeah.
In other words, it has more to do with if all 4 quadrants are included, then you're always, no, maybe not here. No, I'm not going
Oh, no.
not going to be able to do
It's not.
So, and of course theta is all of these divided by 9, right? That's always the next step, is to divide by your 3.
Yeah. So pi over 9.
So theta, you start with that one. Now I got to jump to that one and then that one.
You would add n pi over 3?
Uh-huh.
N pi over 3.
And the other one, you take the second one, you jump to that one, and we know it's going to be the same because the next one we're going to jump to is going to be 8 pi over 3. So it is 2 pi over 9 plus that same. The second equation almost always has the same multiple. It's just a different beginning.
Is there ever a situation where it doesn't?
I don't know. I don't think so. Everyone we've come across, when you have to define it with 2 equations, this part's always the same.
Yeah, okay. Cool.
All right, what do we got next?
Okay, so the next one's find the solutions between the interval of 0 and 2 pi.
Okay.
And the first one is 2 sine 2x plus root 3 equals 0. Did you get that?
Yeah.
Okay.
Whoops, no I didn't. 2 sine...
Oh, plus root 3 equals 0.
Plus root 3 equals 0. Okay, so the first thing I'm going to do, well, let me write it out. All right, so I get sine of 2 theta equals negative root 3 over 2. So tell me where that occurs.
That occurs at 2 pi over 3 and
Sine's positive in the second quadrant.
oh, okay. Then it would be 4, is it 4 pi over 3? Yeah.
Yeah, it's 60 degrees beyond 1, so it's 180 plus 60, which is 4 pi over 3.
4 pi over 3 and 5 pi over 3.
Right. Now, here's the kicker. What's our answer going to be?
4 pi over 6 and 5 pi over 6?
There's 2 additional answers. And the reason being is that theta is in between 0 and 2 pi. But we were talking about 2 theta. So 2 theta is in between 0 and 4 pi. So we have to actually go out to the second unit circle here. And I'm adding, so I get 10 pi over 3 and 11 pi over 3. And now notice that when I divide all 4 of these angles by 2, I'm back in my unit circle. 10 pi over 6 and 11 pi over 6. All 4 of those are in the unit circle.
Okay.
Okay? And that's the trick when you have these multiple angles. And at least this is the way I look at it. I suppose other people could look at it differently, but I expand the domain immediately, and that tells me how far to go out. Now, if this was 20 theta, then I would have to go out to 40 pi. And if you divide each one by 20, you end up with theta being all in the unit circle, but surprisingly, you end up with 4 answers, not 2. In other words, that's the typical mistake, is to find those 2 answers and then convert them to those 2 answers. But if you omit these 2, guaranteed you're losing points on the question. In fact, that's the secret of this question. This question is almost harder than our previous ones where we had to define it as an infinite series. Merely because you have to take their domain restriction and adjust it based on the coefficient that's in front of theta.
Okay.
I suppose you don't necessarily have to do this step. I just think that it helps a lot, because you do have to know to do these 2. In other words, those 2 right there are in the second unit circle. And so I suppose you could just take that multiplier and go that many unit circles. In other words, that means I got to go 2 unit circles out.
Okay.
If this was a 3, I'd have to go 3 unit circles out. 4, 4, and so forth.
Okay.
You still always end up with your final answers in the unit circle. but you end up with more of them.
Okay.
In other words, you make this a 4 theta, and we're going to end up with 8 answers, all of them in the unit circle.
Mm-hmm.
All right.
Okay. The next one is it combines cosine and sine.
Okay.
So it is cosine squared A plus sine A equals 1.
Now, right offhand, this looks pretty tough to solve, right?
Mm-hmm.
What's difficult about solving trig equations is you need everything in the same trig function.
Yeah. So we could convert cos.
Right?
Yeah, I understand what you mean
Cosine
there.
squared A plus sine A or sine squared A? No.
Just sine A.
That's a little puzzling. Okay. That's a new one. I get new ones all the time. Well,
So we could.
cosine A minus 1 equals minus sine A, just using a little algebra.
Okay.
Now, what's cosine squared A minus 1 equal to?
1 minus sine squared A.
Sine squared plus cosine squared equals 1. So cosine squared minus 1 must equal minus sine squared.
Wait, why are we converting that to negative
And
sine?
get everything in terms of sine.
Well, would you not want to? Wait, why wouldn't we convert the cosine squared A into 1 minus sine squared A?
Right off the get-go?
Yeah.
Yeah, no reason. Let's do it that way.
Okay.
Trig, yeah, we're going to get the same answer, but you're right. That makes more sense. Convert it right immediately to 1 minus sine squared. Yeah. Plus sine A. And then you end up with a quadratic. You get the same thing I was going.
Oh, okay.
Yeah. And now what? In other words, this is now equal to 0.
Don't we have to factor it?
Yeah. So
Okay.
if I factor out a sine A, what am I left with?
You are left with negative sine A plus 1.
All that's equal to 0. So is our domain restricted here to the unit circle?
Yes.
Okay. So A is between 0 and 2 pi.
Yeah.
All right. So what's our next step?
Find the zeros.
Yeah.
So sine A would just be 0.
Well, yeah, that's basically our next step, is set them both equal to 0, which means this gets sine A equals 1, right?
Uh-huh.
By the time I do the algebra on that?
Yeah.
Okay, well, where in the unit circle is sine A equal to 0?
Sine A is equal to 0 at
So
pi and 0?
yeah, 0 and pi.
0 and pi.
Thing is always greater than or equal to 0 and less than 2 pi. In other words, it's also at 2 pi, but that's not in our domain.
Okay, yeah.
And where else? Where is sine A equal to 1?
Pi over 2 and 3 pi over 2?
Just pi over 2. At 3 pi over 2,
Oh, it's at negative 1.
negative 1.
Mm-hmm.
1 is one of those where you only have one answer, in the unit circle. There is only one place that it's equal to 1. There's only one place that it's equal to -1 for both sine and cosine.
Mm-hmm.
0, there's always two places. But
Okay.
whenever your sine or cosine is equal to 1, you're only going to get one spot in the unit circle.
Okay.
So our answers are 0, pi over 2, and pi.
Okay. Cool.
You would actually have to define, if that was an infinite series, yeah, that's going to be tough to define. You might need three things, three sentences to define. Let's just look at that. How would you define this as an infinite series? Let's say this was not restricted.
Um.
So over here I got A equals, in other words, if I add a few more terms here,
Mm-hmm.
and then if I add a few more terms here, in other words, every 2 pi, this is going to happen. I guess I can define this easy enough as 0 plus n pi. And the second answer I can define as pi over 2 plus, I got to do the second one in two different terms, don't I? I need another few to add. Let's see, I had pi over 2,
Yeah.
pi over 2. I'm going to add and then I'm adding, where do I get my 11 pi over 2? It's pi over 2, 5 pi over 2, and the next one is adding 4.
Mm-hmm.
So it can be done. Can't it?
Yeah.
I don't think 11 was right. I should have said 9 pi over 2. And then it's going to go up by 4 pi each time. So it would be n times 2 pi, the second one.
Yeah. Okay.
Yeah. Anyway, what else we got?
The next one, well, we could do one of two. Either there's another one where sine and cosine combine,
Okay.
or it's a sine with like kind of a co-function looking problem.
Okay. Either one.
Okay, let's do
Only you know how much material. We got about a half hour.
Yeah. Okay, let's do this one. So 4 sine x cosine x equals root 3.
Lordy. So if we do that.
Yeah.
Now, let's see, I guess, given that sine squared plus cosine squared equals 1, I want to make one of them in terms of the other. Sine x equals the square root, actually plus or minus, the square root of 1 minus cosine squared. So now if I substitute that, I get plus or minus the square root of 1 minus cosine squared x times cosine x equals that. Am I getting anywhere? I think maybe. I might be.
I think so.
don't get too many of these toughies. I don't get too many where you have to use that identity.
Oh yeah. What? That
Now, yeah,
math angle identity.
we're still not quite done, but I guess I can square both sides. Let's see what happens if I square both sides. First of all, if I square both sides, that's going to eliminate that plus or minus. This term into 1 minus cosine squared of x, all times cosine x. No, that's cosine squared x. And this becomes 3/16. So
Did we want to multiply out the cosines and then
yeah, that's
group them?
just what I was thinking. Although I see what this is going to have happen. I'm going to write them like this. I'm going to write the first one over here, minus cosine to the 4th x plus cosine squared x minus 3/16 equals 0. Now I'm going to divide everything by -1.
Okay. So that becomes cosine 4th x minus cosine squared x plus 3/16 equals 0.
And now notice that we are looking at a quadratic in disguise.
Yeah.
At least that's what I call them. It's a quartic, and we're going to have to be a little careful about that. We want to make sure that we end up with 4 solutions probably.
Okay.
But, gosh, can this be factored? I don't think so.
Did you factor out a cosine squared?
No, in other words, I've got it in the format that I want, which is in a quadratic format. In other words, the only way to solve a quadratic, remember you can't factor out cosine squared from every term. What happens to this 3/16? And if I put it back on the other side and then factor it, I'm really just going backwards to what we had previously. So the way to solve a quadratic is to put it in quadratic format. In case you're not familiar with this technique, I'm going to let u equal cosine squared x. So what I really have here is u squared minus u plus 3/16. It's called substitution method. And it's a helpful method to use to recognize that this is merely a quadratic. It's now a quadratic in u.
Yeah.
It's originally called a quadratic in cosine squared.
Okay.
That's the middle term, is cosine squared. Now, the question is, does anything multiply to 3/16 that adds to -1? Why'd they give us such a hard one to start with?
I don't know. Could it possibly be no answer though?
Oh no, no, we can use the quadratic formula here. Let's do that. U equals minus b plus or minus the square root of b squared minus 4 times 1 times 3/16 all over 2. Well, that's 12/16. 1/4, so this thing turns into 1/4. Looking pretty good now. Because the square root of 1/4 is 1/2. So u equals 1 plus or minus 1/2 all divided by 2, which is 1/2 plus or minus 1.
Okay.
Hold on, 1/2 divided by 2 is 1/4. In other words, splitting this up into two fractions.
Yeah.
Okay, so u is 1/2 plus 1/4 is 3/4. 1/2 minus 1/4 is 1/4. So there's our two solutions for u. Now we go back up to this substitution method. Seems awfully hard and complicated, but this is working, and I don't think there's an easier way. So I solve for everything. I've got cosine squared of x equals, we'll start with the 1/4. That means cosine x equals plus or minus 1/2. And now I'll solve the other one where cosine squared of x equals 3/4, which means cosine x equals plus or minus root 3 over 2. And bingo, we have our 4 answers.
Okay.
Well, we don't have them quite yet. We got to figure out these angles. In other words, we need to answer that one. We need to answer that one. So where is x?
X is at the cosine pi over 3.
Was this a unit circle only?
Yeah, yeah.
Okay. So at all the...
So this one has 8 answers in total?
Pi over 3s and pi over 6s, is it not?
Yeah, yep.
So the first one is pi over 6, also pi over 3, 7 pi over 6, 2 pi over 3, for some reason I got lost. I'm adding pi to this now, so I've got, so that's the, you know what my problem was? I tried to do everything at once, which is not the way I'm used to doing it. Let me go back. It confuses my brain. In other words, let me solve that one first, because that's going to produce 4 answers, and then this is going to produce 4 more answers.
So I think it in total produces 8 answers.
Let me erase this so I got room to write. I'm going to have 8 answers. So let's give the first 4 where it's equal to plus or minus 1/2.
That would be at pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3.
And now let's give the 4 answers where it's equal to root 3 over 2.
That would be pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6.
Yeah, and there's my 8 answers in the unit circle.
That's a long one.
It is, and it's also, if it were an unlimited, unrestricted domain, I might have to use 4 equations. I believe I would.
Yeah.
Oh, I'm glad they're restricting them. But this is a kind of a tricky problem. Wow. I wonder if we did it the most efficient way. And we could incidentally test all of these answers. Not that you necessarily want to, but it might be worth testing pi over 3. Is that a true statement? Well, the sine of pi over 3 is square root of 3 over 2. The cosine of pi over 3 is 1/2. So yeah, it's square root of 3 over 4.
Okay.
But it is kind of interesting that we end up with 8 answers to this.
Yeah.
Simple looking equation. I don't know of another way to do it. I think that maybe you got to use that identity.
I think so, because we've been working on identities a lot lately.
Yeah, I don't ever remember doing anything quite like this, where I had to use that identity and then I had to square both sides and then I had to recognize that I was looking at a quadratic and then I almost have to use U substitution. I could actually do the whole problem without technically writing that step down, but that step's kind of helpful. And
Yeah.
then I got to use the quadratic formula to solve this ridiculous quadratic. You know, I actually probably did. Yeah. All my answers, although, yeah, some of my answers involved radicals, so you're not solving this by factoring. So
Yeah.
you do have to use the quadratic formula. Boy, this problem had a little bit of something, everything in it. This should have been a bonus question. That might be the longest problem we've ever done.
Yeah, that was a long one.
All right. No wonder you wanted to jump to that one. I don't know how many more you have. Go ahead. We got a little more than 15 minutes.
Okay. The next one is 2 sine of x minus pi over 6.
All in parentheses like that?
Yep. Plus 1 equals 0.
All right. We're going to solve this the same way we did multiple angles.
Okay.
In other words, we're going to solve for that. And then once we come up with our solutions, we're going to move the pi over 6 over to each one of them.
Okay.
Okay. So work me through the algebra.
You would subtract 1 and then divide by 2 to get negative 1/2.
Okay. This unit circle also?
Yep.
Okay, okay.
Okay.
What's the next thing I should write?
The sign at negative 1/2 and like identify those?
Now the next thing, whenever you have the sign of a variable equals a number, the next step really is to take the inverse sign of both sides of the equation. But also, by definition, that means that x minus pi over 6 has to equal the inverse sign. I haven't been writing it. I've been
One negative 1/2.
Yeah, in other words, what I've been saying is, so where is the sign equal to minus 1/2?
Yeah.
As opposed to technically writing it like this, I should have been writing it all along.
That's okay. I understand that.
Okay, so what are our answers? I keep moving it to the left because I just realized, gosh, who knows how many answers there are here. In the unit circle, what are...
Sine is negative 1/2 at pi over, 7 pi over 6.
Well,
And
it's actually Oh, yeah. What am I thinking? 7 pi over 6
and 11 pi over 6.
yeah. Which is kind of interesting. Let's just comment on this for a little bit.
Okay.
Technically, you get a negative angle when you do that in your calculator. You get a
Okay.
negative pi over 6. Okay?
Mm-hmm.
You don't get 11 pi over 6.
Oh, so it goes
Come
clockwise on the unit
yeah.
circle.
Yeah, so you got to just be wary when you're solving these equations, you're giving positive answers. And your calculator
Uh-huh.
actually give you a negative pi over 6. But that's fine. It's just that negative pi over 6 is not in our unit circle. It's not. In other words, they're saying they started out by writing this, correct, on this problem?
Yes.
Okay. Notice that negative angles are not in that domain.
Mm-hmm.
So in this domain, you gave these two correct answers, 7 pi over 6 and 11 pi over 6. Your calculator actually gives you the -1 unit circle, let's call it. Okay.
Okay.
Now we still have to add this pi over 6. And
So it becomes 8 pi over 6 and 12 pi over 6?
which is 4 pi over 3 and 2 pi.
Okay.
Now, what's the problem now?
I'm unsure.
Our two answers are not inside our domain. And unless they put a less than or equal to 2 pi up there, and they don't usually.
Wait, but 4 pi over 3 isn't in the domain?
No, 4 pi over 3 is in this domain.
Oh, okay.
In other words, when they restricted the domain, does it read exactly like that?
Yeah, well, it says find solutions on the interval, and then the interval is 0 with a bracket and 2 pi with a parenthesis.
Okay, good. So this 2 pi is not an answer,
Okay.
but 0 is. In other words, if I subtract 2 pi,
Mm-hmm.
why didn't we find that? In other words, how can I say this? Again, you can look at it like this. If x has to be between 0 and 2 pi, then x minus pi over 6 has to be between minus pi over 6 and 11 pi over 6. So all I did
Okay.
was subtract pi over 6 from all three. Okay? So
Okay.
now when we're solving for that, we really need to do it in that domain. And 11 pi over 6 is not in that domain, but minus pi over 6 is.
Mm-hmm.
So those were really my two solutions to this problem. And now when I add pi over 6 to both of those, I get 0, and I get 8 pi over 6, or 4 pi over 3. So
Okay.
these are my two solutions. And I don't know that you necessarily have to do that, but it's kind of helpful.
Yeah.
Because when you go to solve this equation right here, you can't see where I'm pointing, but this equation, when I go to solve this equation, I have to know whether my answers are 7 pi over 6 or 11 pi over 6, or minus pi over 6 and 7 pi over 6. It's
Uh-huh.
either those two or it's these two, and the only way I can really choose is by knowing that exact domain.
Okay.
not the top one. You're not
Yeah.
using the domain for x, although you will notice in our final answer, we're still inside this domain.
Uh-huh. Okay.
But in order to get the 0, we were going to leave that 0 out if we would have done it the regular way here. And in order to pick it up, I've got to pick up that right there as one of my solutions instead of 11 pi over 6.
Okay, I understand that.
That's a little tricky. Whenever you have stuff inside the argument, you have to adjust your domain. Whether it's 2 theta or 3 theta or 5 theta or theta minus pi over 6. That means the domain for this is not 0 to 2 pi.
Okay.
All right, what else?
Okay, so this one is cosine of 2x equals sine of 2x.
You could use your calculator. What would you do?
I would set x equal to something.
Actually, set y equal cosine 2x or x.
Okay.
You don't really need the 2x. No, you could make it 2x and set y sub 2 equal to sine of 2x, and wherever they intersect, that's your solution.
Okay.
Okay? That's with a calculator. I don't think I want you to solve this with a calculator.
No. I'm unsure on how to go about this problem.
Well, got a bunch of double angle identities where we can turn that into some number of sine squareds.
So that could become, I'm just trying to remember the double angle identity for that one.
So I think it's 1 minus 2 sine squared x.
Yeah, or it's cosine squared minus sine squared x.
Yeah, or
Either.
I can put it all in cosine squared also. The reason there's 3 identities for this is so you'll have all 3 options available when you need them.
Okay.
The question is, sine of 2x is 2 sine x cosine x. Is it not? Yeah.
Yeah.
Solve that. Don't tell me this is going to be one that you got to use that identity again. I bet you do, because we had to use that identity
For cosine x when it's not squared.
we had sine x times cosine x. We used that identity, remember?
Yeah.
That really tough problem?
Uh-huh.
Gosh, is there any other thing to do with sine of 2x? You could call it the sine of x plus x, use the sum and difference, but that's still going to give you some combination of sines and cosines. It's still going to give you this, in fact.
Yeah.
Well, let's proceed with this and see what happens. I'm going to put everything in sine. Means this becomes square root of 1 minus sine squared x. Okay, now I square both sides. What do I get? Help me square both sides here. In other words, I get a radical sign.
Uh-huh. You get, for the left side, you get 1, left side you get 1, would it be plus 4 sine to the 4th x?
No, it's minus. Think of it as a minus b squared. In other words, I'm squaring that. and I'm squaring this. And when you want to square something quickly, think of a minus b squared is a squared minus 2ab plus b squared. So the middle term is 2a times b. Well, that's 4 sine squared x. And if I square this term, it's plus 4 sine to the 4th x. Okay?
Okay.
Now on the other side, I just have to square both terms, and I get that times that. Now if I distribute and simplify, I'm going to see a lot of nice things happen.
Okay.
I almost feel like I'm going the long way here unnecessarily, but I can't see any easy.
Yeah, another route to go about it.
Yeah, there may be missing something, but that's okay. There's more than one way to like that. Now I've got, hold on. What do I got? I got a total of 8 sine to the 4th x minus 8 sine squared of x plus 1 equals 0.
Now, is this a problem where you would substitute u for sine squared?
Yes. In other words, this is another quadratic, and it's also a quadratic that's not going to factor. Okay. No. So you're going to have to use the quadratic formula. But yeah, turn it into 8u squared minus 8u plus 1 equals 0. Use the quadratic formula. I guess you end up having to use the quadratic formula because your answers are usually going to come out with a square root of 3 over 2 in it, right?
Yeah.
And that's not the kind of answers you get when you factor. It's the kind of answers you only get by using the quadratic formula. So do that and then go back and solve for u twice. Notice you're going to get 2 answers. In other words, by the fact that we're looking at that as a quadratic, we're going to get 2 different u's.
Okay.
U is equal to sine squared x, so you're going to have to take both u's that you come up with, and plug them in, and then you're going to end up with 4 answers for that, because you're going to take the square root of both sides, and you get a plus or minus square root of u. So there's 4 spots where that's going to be true, and then there's going to be 4 more spots where your other u that you come up with. So this is another one where you should have 8 answers.
Okay. Okay. Yeah, I get that.
Yeah, and this should solve exactly the same way as the other one does. But you got to use the quadratic formula, and you got to use, boy, this really makes me think that I'm taking the long way, because I don't know.
That's okay. I can ask my teacher on it too and see if there's a shorter route that he sees.
Do these. If you discover that there's an easier way to do these, please enlighten me the next time we have a session. Just so I'll know.
That's okay. Okay, cool. I think I know how to go about this problem.
This way works. I'm surprised they didn't introduce you to using quadratics a little bit easier. In other words, they could have at least started out by saying sine squared x minus sine x minus 2 equals 0. In other words, let you solve that as a quadratic by factoring it.
Oh, we've done those. Yeah.
Oh, you've done those.
I haven't seen those.
So this is just a step higher, a step more complicated. Yeah.
Yeah.
Okay. All right. Well,
Cool.
maybe that's the way to do them, but at least it's a way to do them if you can't
Yeah.
find any other.
I'll ask my teacher on it and see if he has another like way, maybe.
Okay. Yeah, please do. I'm curious to know because there may be an easy way that I'm just completely overlooking. My way seems awfully hard, but
Yeah, but it does produce the right answer.
yes. No, I wasn't too concerned that it wouldn't. But
Nope.
all right, Nick.
Okay.
Have
Cool.
a good week. I'll talk to you next time.
Thanks. You too, Miss Khan.